Welcome to Day 4, Microarchitecture. Today we'll be talking about inductive biases, that is, generalizations, that come from small-scale operations. A bit more about me. My name is Zach Pitko. I'm an associate professor at Carnegie Mellon University in the Neuroscience Institute and affiliated with the Department of Machine Learning. I'm also the associate director of the NSF Institute ARNI, which stands for Artificial and Natural Intelligence, which is an institute dedicated to neuro AI and is one of the primary funders of this course itself. I'm also the director of this course, and I am delighted to be bringing a day worth of material to you with the help of my amazing colleagues and content creators. I'm also a big fan of art and music, and we could talk about that another time. So the first few days of the course dealt with the big picture in neuro AI and started to establish what it means to compare brains and machines, the tasks that they're doing, the networks that they use. And now, in the next 5 days, we're going to talk about what computational structures in brains and machines can help them perform and be intelligent, help them generalize. So we'll focus on architecture and learning at different scales. Today we'll talk about microarchitecture, tomorrow is macroarchitecture, and then the next day is cognitive structures, in particular neurosymbolic structures. After that, we'll return to learning, where we'll talk about microlearning, aka plasticities, small-scale synaptic rules, and macrolearning, which is more like the objectives and curricula that you follow in order to achieve your goals. So let's dive into microarchitecture, the topic of this day. What is microarchitecture and how can it support generalization? We'll learn that through 3 tutorials focused on sparsity, normalization, and attention, which are all operations that are very commonly seen in both brains and machines and have certain computational consequences. So what is microarchitecture? Well, these are small-scale structures that have computational consequences. Examples include small circuit motifs, ways of connecting specific dedicated neural units together. Also, the neural properties that give rise to their nonlinear transfer functions or activation functions, that counts. And then there may be even finer scale things inside of a neuron, including the internal states of either the neuron as a whole or even synapses. So there are many properties of microarchitecture that we could talk about, but we're going to focus on a subset of them today. The important reason for talking about microarchitecture at all is that it's a form of parameter sharing. And parameter sharing is critical because generalization requires it. Generalization, in a sense, requires explaining more things with fewer things. And that implies rules. There are computations that share the same parameters. This is also true for understanding. You need to share parameters to have an understanding, because if you just have a completely general nonlinear dynamical system with separate mechanisms for every individual computation, then you can't explain anything. So we really are focused on parameter sharing. The classic example of parameter sharing in AI is the ConvNet. Convolutional networks share filters across space and time, or sometimes other features. And that's really helpful for a translation invariant world, or a world with other kind of group invariances like rotations. The problem is that's not the way the brain does it. And so there's an important element that's missing. And in fact, the brain is more flexible than using this parameter sharing. It's biologically implausible because the brain has no mechanism of copying weights from one location to another location, by and large. And in fact, the brain does not do that because when you challenge the brain with a world that is not, in fact, translation invariant, if the statistics are no longer stationary, as Lee and DiCarlo showed in 2008, the brain adjusts and it no longer creates the same invariances that you would expect from translation invariance, but it actually learns to be sensitive to whatever thing is now consistent across space and time. It's a really cool study. Even in the ConvNet, later layers are not translation invariant anyway. They're either locally connected for a while, and then the end, they're fully connected. So there are some crucial properties that are not just blindly copied and parameter shared across all space. So we need to look more deeply for notions of parameter sharing that will apply across all these systems. And one very general notion here is the idea of an algorithm as parameter sharing, a kind of symmetry. That is, you're doing the same computation for all sorts of different inputs. So if you think about classic algorithms in general, you might have a bubble sort or an L1 regularization, or even gradient descent and recurrence, belief propagation. These are all named algorithms that are named because they have some property that you do over and over again. And so in L1 regularization, you penalize the activation or some quantity with the same penalty for all of those variables, all instances of those variables. In recurrence, you have a neural network which is applying the same computation every time step. And you can consider this to be, if you can unroll it to get an equivalent feed forward network with its own weights between these new layers that you've just unrolled, but those weights are copied, they're shared. And so it's a mechanism that is providing an algorithm over time that is consistent. This provides us with an interesting way of thinking about the brain and biological plausibility for an algorithm, and that is hardwired structure with shared parameters. Genetics, whatever you inherit, that provides a structure. It gives you different kinds of cell types and a specific developmental program which initializes the way your brain is wired up. It has some canonical learning rules that result from that program. And it has also plasticity rules by which they can continue to update their connections. You also have large scale structures that emerge. Everybody's brain has largely the same big parts, even though the details are very different. And that includes things like how one brain area modulates another brain area. These are all ways that the algorithm can be hardwired and parameter shared across space and even across people. AI has tried over the years to keep updating the algorithms, and really these are microarchitectures that have been potentially useful for computation. In 1943, the earliest example of using brain-like computing to solve problems was the McCulloch and Pitts neuron, which basically used kind of neuro-style logic gates, which were binary and used summations and thresholds. Later, those were softened to give you sigmoid functions, and their interesting theorems were proved about universality, which we'll return to. But then, when deep learning really started to take off, people started using rectified linear units, which were even simpler. They were fast to use, and that had a major computational benefit and had very powerful consequences. But then when you were training these, there were limitations and you found vanishing or exploding gradients. And so other microarchitectures were introduced, like the long short-term memory by Hochreiter and Schmidhuber, which tried to solve that problem. Others tried to include even more brain-like structures using spiking neurons and neuromorphic computations. And the most current version, I would say, of a microarchitecture that people are using a lot right now is self-attention in transformer networks. So all of these different microarchitectures have different advantages and they provide different performance benefits. So are these just lucky, or there are some principles behind it? Or is this a consequence of a hardware lottery where the best thing to use at a given time is a consequence of the machine you're going to run the algorithm on? These are important questions that still have to be answered. One of the most prevalent microarchitectural elements that people played with is activation functions. Nonlinear activation functions are critical for any neural network because if you have only linear activation, then you get much less benefit from a deep network. People started with threshold units and sigmoids and exponential linear units and different variants of these, or even learnable ones. And so then the question is, why? What do these activation functions do? Do they have any benefit in their differences? Well, a lot of them are universal. There are theorems that prove, initially with sigmoids and later with monotonic functions, that if you have a sufficiently wide neural network, even a shallow one with one hidden layer, you can approximate any function as long as you have these simple nonlinearities, which is great. That universality means that these are very powerful, but it doesn't tell you that it's easy to do, easy to find, or use a reasonable number of resources. You may need arbitrary width of these networks in order to actually accomplish that goal. And their massive expressivity is actually too strong. It means it's too powerful and it can overfit even random permutations of the labels that you might give it. So that means that it doesn't have a great inductive bias. It's not going to necessarily just by itself guarantee that you're going to generalize well. People have, however, looked at generalization properties of some of these networks and found that in the limit of large overparameterization, like massively wide networks, there are some things that emerge naturally. In particular, you get a certain smoothness out of these large networks. This is the work by Joao Bruna and colleagues and Ankit Patel and colleagues, thinking about what inductive bias, what implicit bias shows up when you have a lot of ReLUs, each giving you a little bit of change of slope at a specific point. So that smoothness is very helpful for functions that you want to be smooth, and it emerges naturally from having many more parameters than you have data points to constrain them. So your initialization, which turns out to be smooth in many of these initialization cases, that's the thing that gives you this regularization. So these 1D activation functions, they have some nice properties that do give you a good inductive bias for certain kinds of problems. But 1D activation functions are not the end of the road, and people have considered more. For example, a very flexible activation function is called the network in network, where you have a little mini neural network that transforms a set of inputs into an output and copies that throughout the entire network. I've worked on a variant of this with a couple of colleagues to look at two argument variants of this, where every neuron actually has two inputs, like an apical and a basal input, which are things that relate to neuroscience. You see these different kinds of inputs. And if you learn those networks, you actually find some pretty consistent properties, in particular, like an XOR type of thing that just shows up for free when you train them. Real neurons have these multiple different kinds of inputs. So here's a drawing from Ramon y Cajal, the great anatomist, and our modern version, which is now 3D reconstructions of scanned brain tissue, which have these incredibly intricate dendritic inputs. So these trees that provide the inputs, they are not just linearly weighting the inputs the way that conventional deep networks do. And these are maybe rightly thought of as each neuron being its own little neural network too. So what do these activation functions give you? What can they do? And we will see in these tutorials that having specialized functions can actually be of a big benefit. And perhaps that's what some of these neurons are actually providing. Another thing that we're not really going to have in a tutorial, but can be very important for microarchitecture and is certainly happening in the brain, is that these neurons are not just memoryless units. They have an internal state, and that latent state can do temporal filtering and adaptation. It can make all sorts of parameters change that if you were just looking at the features, you wouldn't think that these units were actually consistent over time, that something about them is changing. But their parameters are static. It's just when they're given a nonlinearity and an integration with an interesting history, then more complicated things can show up that allow these networks to shift their sensitivity appropriately for the input. And this is something that has been very poorly explored in artificial neural networks, but I think has good potential for the future. And this is true even at the level of individual synapses. So neurons' connections between them are not single numbers. They are themselves complicated machines with a whole bunch of structure. For example, that which was described by Bena and Fuzzi showed that you can have metaplasticity which is essentially a learning rate that depends on your history that can create much longer lasting memories and prevents some catastrophic forgetting. And people have also explored eligibility traces, which are related to this, saying when should you be willing to learn at this synapse? So these states can have big impacts in preventing catastrophic forgetting and improving some credit assignment. These are, again, things that are relatively untapped. So, how do all these things help? How do they improve our generalization? Well, this is something that's going to come about by really a combination of architecture and learning, like the rules that update the synapses and update the properties of these networks. They cannot be fully disentangled. But today, we're going to focus on some of these architectural properties. And so we'll learn about some things that you can understand in isolation. So we'll have three tutorials today: sparsity, normalization, and attention. So let's talk about sparsity first. Sparse, what is that? It just means rare. And there's a lot of ways that something can be rare, and different things can be rare. You could have rare activity, which is a very common notion of sparsity. So you can have two kinds of activity sparsity: one which is population, that is, only a few neurons are active at a time and the rest are zero, or lifetime sparsity, talking about one neuron that is not on very often. You can also have sparse interactions between units or nodes in your neural network. And that essentially creates a graph, not a fully connected graph, but a sparsely connected graph. And closely related is the idea that you could have sparse features. That is, not every part of the input affects every hidden unit. And so you have something sparse, compact, maybe localized, maybe spotty, but these are things that can be described as interactions between nodes that are sparse. Why do we care about sparsity? Well, sparsity is really a compression. And compression is good because it allows us to focus parameters on the parts of data that need them. This is useful in our world because our world is well described as having sparse causes. Objects are rare, their interactions are rare. And that means that sparse representations can be more interpretable as causes and therefore better generalizers, things that are focusing on the elements of the world that could change, that could influence us, or that we can influence. And having those sparse representations, even if they're not perfectly one-to-one with the causes in the world, can enable sparse interactions between those represented causes. This is a theory about how the brain is working and how machines aspire to work. And those sparse interactions can enable efficient computation, just because you're not propagating information in as many wires between things. But it's also likely to be useful just from a performance perspective because it's matched to the world, which is composed of these sparse interactions. Not everything is interacting with everything else. How do we make something sparse? How do we get the activity to be sparse or the connectivity to be sparse? Well, there are different mechanisms, and some of these can be directly related to microarchitecture. Optimization, for example, is you say, well, I'm going to penalize the activity of the neurons. And that could be an internal state that just says, here's a cost associated with activation. But you can actually relate this. You can have a structure, an architecture, a microarchitecture, which will impose L1 regularization or other kinds of regularization. So that's interesting. And microarchitecture can do other things as well. For example, computing spatial or temporal differences. Like these two little tiny circuits here, the left one, the feed-forward inhibition, this provides a way of doing a temporal difference. So you have the bottom neuron, which is active, and it activates the top neuron, but at a slight delay, it activates the middle neuron, which then inhibits or suppresses the top neuron a little bit later. So it gets turned on and then immediately turned off, giving you a temporal derivative. And likewise, the right circuit gives you lateral inhibition, which computes a spatial derivative. So these are microarchitectures that that can give rise to sparsity. You can also do this by nonlinearities, for example, a high threshold, which we'll discuss in the tutorial. Or normalization is another way of getting this, which we're going to see next. And in fact, normalization is the topic of the second tutorial. Normalization by itself is basically you have some feature vector and you divide it by some function of the whole of that feature vector. And it could be based on division of parts. There's a lot of functions that you could use here, different norms, but this is the essence of the normalization idea. There are many variants that are currently in use in AI. People often use batch norm, which is really dividing all of your data to make sure that it runs in that all the data that you're currently training on to make sure that it falls within a given range. But that's not something which is online actionable. You need to have a whole batch in order to do that. So then Hinton and colleagues proposed layer norm, which was using just the activations that you have right now, normalizing them as a maybe as a proxy for batch norm. And then subsequent work said, well, maybe we don't want to use the whole layer, but some local normalization, leading to different variants of divisive normalization. All of these are currently in use and there are many more of them too, have pros and cons in the use of AI. And we'll look at some of these. In brains, normalization is the canonical example of a canonical operation. And you see normalization all over the place. Many different papers thinking about how it can explain lots of different properties that we see in the brain and in individual neurons. So, why are we using normalization both in AI and brains? What are its benefits? Well, we have the benefit of allowing propagation of signals to be stable as they go forward, neither blowing up nor shrinking down. And that also can be used not just for having signals there, but having information in those signals, maintaining informative forward propagation, avoiding things like rank collapse or avoiding noise problems. It also allows us to do backwards propagation through gradient backprop and gradient descent. And so adding normalization layers allows us to avoid some elements of vanishing and exploding gradients, which would prevent learning. And there are also cases where normalization is just the right thing to do if you want to infer some property of the world. For example, if you think about vision, we often have a material that is reflecting light. And so we might care about the material. For example, we're looking at some picture of some apples and we'd like to know, are they ripe? And in order to do that, you can say, well, hey, they visibly look red. So this visible image V is a red image. But you can also see that there's this global lighting, which is red. And the apples don't look red relative to the green leaves or the leaves we presume will be green. We know this because we are presumably doing some divisive normalization on our own to remove this global lighting effect and extract the behaviorally relevant material properties. So tutorial 2 is going to look at how normalization shows up and what benefits it has. We'll start by looking at what difficulties you have in learning 1 over x type divisive operations just using a generic neural network, which motivates the benefit of having a dedicated operation, some microarchitecture that can do normalization. And we'll look at the performance benefits, such as lower sample complexity that come from having the right normalization, and also look at efficient coding to make sure that we're actually carrying forward the information that we would need for downstream computation. And then our final tutorial of the day will be attention. Now, there are many different notions of attention that have arisen in brains and machines. We start with the notion of attention from psychology, which is awareness, the idea that you are attending to or focusing on one particular thing out of many. There's a theory of how that works, which is a mechanism, a neural mechanism potentially, which is called the spotlight theory of attention, which essentially says that you are multiplying certain inputs by some gating. And you can also view this as another variant of normalization where you turn down some of the elements. This idea of multiplicative gating has been considered in artificial networks for a long time, since the parallel distributed processing book in '86. They proposed, in addition to their regular neurons, what they called sigma pi neurons. The sigma stands for sum, and the pi stands for product. And the idea is that instead of taking a function of a weighted sum of the inputs, you take a weighted sum of products. For example, R1, R2 plus R2, R3 plus R1, R3. That kind of structure can help you with computing certain operations that you might need. And the interesting thing is that they recognize that this gives you essentially a dynamically programmable network where the connections between one unit and another unit downstream can be adjusted by some other third units. This idea of multiplication shows up in biology. This spotlight of attention, it shows up not just in attention, but in many other microarchitectures. One prominent one is when you're trying to locate where sound is coming from. And it turns out that in the brain, this comes about by multiplying the signals coming from your left and right ear. And the way that that's done is by coincidence detectors in this particular machine called the calyx of Held, which is the biggest synapse in the brain. It's accurate down to microsecond precision. It's a multiplication. And then another prominent one here is the Reichardt motion detector, which is thought to explain how we detect movement and explain this interesting illusion called the reverse phi illusion, which makes these boxes look like they're moving in different directions, even though if you stare at them closely, you realize that they're just staying exactly where they are. But little deviations at the edge are making it look like they're moving specifically for this multiplication mechanism that we have in our brain, a combination of multiplication, time delay, and subtraction. In machine learning, this basic idea has now been used to great effect. And so a lot of the tutorial 3 is going to be focused on how that's used in machine learning, beginning with this core idea of attention in machine learning being really, again, a gating, where you have some variable z, which determines how the different inputs x are routed to the output y, what weights they're assigned. The weights end up being a product of whatever their regular weights are times z. And then a variant of that is self-attention, which has been very powerful in language models and vision transformers. Self-attention really is using two multiplications with a normalization in between them. It's often talked about as a query, key, and value, but I think it's helpful here to think of this as you see the XX transpose over here. That right there is a product of all the pairs of inputs that you might have, and there's some weighting associated with them. Then the softmax is really a normalization that ends up sparsifying which ones of those products are going to be the ones that carry information on. And then again, the output of that softmax is the gate on the values of which x's are going to move forward to the next layer. So you can see in this self-attention, we have these three canonical operations of sparsifying by normalization of products. So tutorial 3 is going to show the relationship between this kind of self-attention and context-dependent graphs, these sparse graphs which are changing how different variables are communicated downstream. And it will also show you the generalization power, what inductive bias these self-attention modules have on sparse computational problems, which gives us insight into what kind of problems they'd be good at and potentially what kind of problems they would struggle with. So this can help us think about what principles of intelligence we need for what types of problems. So I hope you enjoy this tutorials